Bismillahirrahmanirrahim. The topic that's we're going to cover here is the simple solve examples uh, to design a vertical curve and try to summarize it in an easiest manner so that the student could understand it very easily. So first, let's go to example 3.2. Uh, it says that an equal tangent vertical curve is to be connected to be constructed between the grades minus 2% and 1%. The PVI is at 110 plus 0, and at elevation 420 feet. During crossing the roadway, the elevation of the roadway at station must be design the curve. So what first of all we'll try to write down the data. The data says the grade 1 minus 2% means 0.02. G2 plus 1% means 0.01. Station at the intersection of vertical curve is 110 and its elevation is 420 feet. And the crossing is at station of 200 feet and has elevation 200 feet. So when we been asked to design the curve means to find the length of the curve. To find the length of the curve, that's what that is required in this question. So let's try to have the diagram so that we can understand. So this is a sag vertical curve when 2% grade meets the 1% grade. And at this crossing point, there is a street that is being crossing and that is 200 feet from this this point of intersection. And this is length, and this is the PVC, and this is PVT, and all that. So what you do, first we have a general form of an equation in which elevation along any point of the curve is given by this parabolic equation ax squared plus bx plus c. And a is simply the difference of the grade divided by 2 times the length of the curve. So just plug in the values given the data, we come across that the value of coefficient A is 0.015 L. The coefficient B is simply G1, that is now minus 0.02. And the coefficient C is elevation at the start of the curve. And this can be determined by knowing the elevation at PVI. And if you add this much of distance, this distance is simply G1 L by 2. So that's how it is being written here. So in this scenario, if we plug in the value, we know that PVC is 420 and G1 is 0.02 and L upon 2. So this becomes Y PVC is 420 plus 0.01 L. So once you do this, now we are going to put this equation, put this parameters in a curve, this equation, and we'll see that sorry about this. So what we do this, we know that y 0.015 and x square minus 0.02x plus 420 plus 0.01, and add so that, and now if we want to know the value of x, x is simply 11,200 minus 11,000 plus L by 2. So the value of x is being placed over here. So once all these values are known to us, what we are going to do is just substitute in this equation where y is equal to 0.015 Lx square minus 0.02x 420 plus 0.01 L. And we know that the elevation at this point of the curve where the street crossing is 424.5. That was given and this is here at this point. The street crossing, that's why we have taken y as 424.4. The rest we have coming from the equation, and by just plugging out all these values uh, and solving it accordingly, we find we can simplify that this equation is now the 0.00375 L square minus 5.5 L plus 600. And since this is a quadratic equation, we have two solutions. The length of curve is 1348 feet, and the length of curve is 119 feet. And out of this value, this one L is equal to 119 seems illogical, because here the statement says the crossing, the elevation of the roadway is it's 200 feet. So I mean, whatever is the length of curve, it should be more than 200 feet. Why? Because there is a curve that is at least so long that 200 after 200 feet before termination of the curve, there is a crossing. So the curve must be more than 200 feet. That's why this value L is equal to 1195 feet is discarded, and logically this is the value, or the actual length of the curve is 1348 feet. So this is what example 3.2 asks you, and we have completed this problem. So for this next, we'll have another video.